Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome to the debate. Today, we are tackling a fundamental, honestly, and often hair-pulling challenge in biomanufacturing.
Yeah, managing the notorious lot-to-lot variability inherent in complex raw materials.
Right. If you have ever been on a production floor when a massive bioreactor just suddenly fails on, say, day 10, and millions of dollars go down the drain simply because a new batch of raw materials was just slightly off, well, you know exactly the nightmare we were talking about.
It is the exact kind of unpredictability that keeps process engineers awake at night. I mean, we are specifically looking at materials like peptones and corn steep liquor here. These are agriculturally derived, biologically rich soups, and because they come from nature, they are wildly inconsistent from one batch to the next.
Exactly. And the source material we are examining today proposes a fascinating, highly structured 14-day solution kit to solve this exact problem. The methodology is straightforward but technologically sophisticated. First, you perform fluorescence spectroscopy, specifically excitation emission matrix or EEM fingerprinting on the incoming raw material batches. Then, you take that complex spectral data and use principal component analysis, PCA, to group the lots into 3 distinct productivity clusters.
High, medium, and low.
Right, high, medium, and low. And finally, based on the cluster a particular lot falls into, you adjust the feed-forward glucose-to-nitrogen ratio in your standard operating procedure.
And it is the interpretation of this methodology that brings us here today. Does this spectral fingerprinting and PCA clustering offer a robust, definitive solution to the deeply embedded problem of raw material variability? Or is it an overly reductive quick win that simplifies highly complex biological inputs into basic, rudimentary categories?
Well, to put my cards on the table, my position is that this 14-day protocol represents a highly effective, data-driven optimization that successfully neutralizes variability, which is clearly evidenced by its concrete results.
And I will argue that reducing deeply complex materials into 3 simple buckets and tweaking basic operational ratios is a reductive patch that addresses surface-level symptoms rather than the underlying inconsistencies of the raw materials.
Let us start with why I view the framework presented in our source material as an absolute triumph of process engineering. We have to ground this in the reality of what we are dealing with. Peptones, for example, are derived from enzymatic digests of animal or plant proteins. Corn steep liquor is a byproduct of corn wet milling. Their chemical makeup depends on the season, the crop yield, the geographical origin, specific processing conditions, the list goes on. Historically, the industry has relied on basic vendor certificates of analyses which are practically useless for predicting how living cells will actually react. We have always struggled to predict performance until the batch is already running.
Right. And by the time you see the cell viability dropping in the reactor, it is far too late to do anything about it.
Precisely. What this material presents is a brilliant synthesis of analytical chemistry and data science to get ahead of that failure. By using EEM fluorescence spectroscopy, we are basically shining a highly specialized, multi-wavelength light onto these incoming batches and measuring exactly what glows back. We are capturing a highly sophisticated fingerprint of specific amino acids, vitamins, and complex organic molecules in real time.
The analytical side of this is indeed beautiful. Capturing the autofluorescence gives us a magnificent, high-resolution topographical map of the biochemical reality.
But here is the critical pivot from science to engineering. Raw spectral data, a 3-dimensional map of millions of data points, is practically useless on a manufacturing floor. You cannot hand an operator a massive data file and expect them to make a split-second processing decision. That is where principal component analysis comes in. For our listeners, think of PCA like trying to summarize a 1,000-page novel. You do not read every single word to the operator, you extract the major themes. PCA condenses this massive data into highly actionable insights, allowing us to categorize the material into high, medium, and low productivity clusters. From there, modifying the glucose-to-nitrogen ratio is deployed. Achieving a 50% reduction in outlier batches and securing consistent peak titers, all within a 14-day turnaround, is the hallmark of an optimal evidence-based system. It takes chaos and imposes reliable order.
I hear you, and the empirical outcomes detailed in the material are certainly impressive. Having your failure rate is undoubtedly a valid quick win, but we have to look very carefully at the language and the conceptual framework here. A quick win inherently admits that the solution is incomplete. If you have saved half of your lost batches, you are simultaneously acknowledging that the other 50% of your failures are completely unaccounted for. My deep concern lies in the aggressive reductionism of this approach.
Reductionism is exactly how engineering solves complex problems. We isolate the variables that matter most.
But we are dealing with biology, not a purely mechanical system. We are talking about categorizing inherently complex raw materials, substances that contain thousands of distinct molecular entities, varying peptide chain lengths, unpredictable trace minerals, into merely 3 clusters: high, medium, and low. To use PCA to squash the vast multidimensional complexity of a biological fingerprint into 3 operational buckets is dangerously reductive. Furthermore, the operational response, simply adjusting the sugar and protein diet in the reactor, is an incredibly blunt instrument. It risks masking the deeper structural variations of the raw materials. You might be forcing the cells to hit a specific production target by pushing the carbon and nitrogen balance, but you are not genuinely standardizing the biological quality. You are paving over a pothole rather than fixing the foundation of the road.
Let us dive right into that specific critique, starting with the application of PCA and this idea that we are losing essential biological complexity. The fundamental reality of biomanufacturing is actionability. PCA is not just squashing data randomly. It is an elegant mathematical necessity. By calculating the principal components, the algorithm is objectively finding the exact features in the spectral fingerprint that correlate most strongly with the variability we care about. In this case, that is productivity.
It correlates with the loudest variability, yes, but not necessarily all the biologically relevant variability.
It captures the variance that dictates whether a batch succeeds or fails. By drawing mathematically derived boundaries for high, medium, and low, the spectral data is transformed from an academic curiosity into a functional parameter. We can integrate this into a standard operating procedure in just 14 days. If we do not reduce the dimensionality of the data, the spectroscopy serves no practical purpose on the production floor. We would just be admiring the complexity while our batches continue to fail.
I come at it from a different way. The entire point of adopting a sophisticated analytical tool like EEM is to illuminate the nuanced biochemical reality of your raw materials. You are capturing the subtle signatures of fluorophores like tryptophan and AHDH that dictate intricate cellular metabolism. When you take that rich data and force it through a PCA algorithm solely to spit out 3 buckets, you are stripping away the exact complexity the spectroscopy was meant to capture. You are discarding the secondary and tertiary principal components, the minor themes in your novel analogy that might explain why some batches scale perfectly while others suffer from strange impurity profiles.
But if those minor themes were actually crashing the process, the PCA model would pull them out as primary drivers of variance.
Not necessarily. We are treating corn steep liquor as if it operates on a simple linear sliding scale of good to bad. Biological systems do not work that way. A batch might be categorized as low productivity not because it lacks basic bulk nutrients, but because it has a slightly elevated concentration of a specific trace inhibitory compound. Lumping it into a broad low category completely destroys the resolution required to understand the material. You are blinding yourself to the actual mechanism of failure.
I see why you think that, but let me give you a different perspective. The justification for the clustering is found directly in the result's consistent peak titers, regardless of the raw material origin. We are not conducting a purely academic exercise in characterizing every single trace molecule. We are trying to control a commercial manufacturing process. The PCA clustering works because it successfully predicts performance at the macro scale. If the loss of secondary complexity were truly detrimental to the process, we would not see a 50% drop in outliers, and we certainly would not see consistent peak titers across completely different agricultural origins. The mathematical reduction is a calculated filter that separates the signal from the noise. The categories are robust because they map directly onto the metabolic capabilities of the culture.
Mapping onto the metabolic capabilities brings us to the actual intervention proposed in the material, which is where this methodology feels particularly strange to me. Adjusting the feed-forward glucose to nitrogen ratio based on these clusters is a massive oversimplification. Peptones in corn steep liquor are not just basic sources of bulk carbon and nitrogen. If they were, we would just use chemically defined media and avoid agricultural byproducts altogether.
We use them because they provide a rich nutritional baseline that is incredibly difficult and expensive to synthesize from scratch. Exactly. They provide complex peptides, essential growth factors, vitamins, and trace elements that dictate cellular signaling and protein folding. Modifying a basic sugar and nitrogen feed is a simplistic lever to pull. If your EM fingerprint identifies a low-productivity batch because it is deficient in a specific class of low molecular weight peptides, simply dumping more bulk glucose into the bioreactor does not solve the biological deficiency. It is like telling someone with a severe vitamin C deficiency to just eat more bread because they need energy. It merely pushes the metabolism along a different, potentially stressful pathway to force the final titer. That is an interesting point, though I would frame it differently. The adjustment of the nutrient feed is not an arbitrary tweaking of bulk ingredients. It is a precise, targeted response to the metabolic state induced by the specific raw material cluster. What the material demonstrates is a highly practical application of the data. If the PCA indicates a raw material lot will drive the culture toward early senescence or rapid, inefficient biomass accumulation, altering the feed-forward ratio directly compensates for those inherent deficiencies.
It compensates for the output, not the deficiency itself.
By manipulating the fundamental carbon and nitrogen flux, you are giving the cells the exact metabolic constraints they need to channel their energy toward product formation, the peak titer, rather than wasting it. The SOP adjustment effectively harmonizes the culture environment. We use the high, medium, and low categorizations to establish a baseline, and the glucose and nitrogen feed acts as the counterbalance. It is an elegant engineering solution to a biological problem. You do not need to add the specific missing peptide if you can steer the metabolism to succeed without it.
I'm sorry, but I just don't buy that. Let me tell you why. Tweaking basic macronutrient feeds based on a broad categorization is entirely reactive. It manages the symptom rather than standardizing the incoming quality. When you alter the C to N ratio to force a specific peak titer from a suboptimal batch of peptones, you are inevitably altering the physiological state of the cells. Yes, you might hit your peak titer metric. You get the volume of product you wanted, but at what cost to the product's quality?
The material clearly states they achieved the desired outcomes reliably across batches.
But biological complexity cannot be outsmarted just by turning up the glucose dial when your model says the lot is low quality. Are you increasing host cell protein expression? Are you altering the glycosylation profile of your biologic drug, which dictates how well it functions in a human patient? It assumes that bulk feeding can flawlessly substitute for the complex micronutrient profile of the raw material. That is a fundamental misunderstanding of biological systems. Masking a complex deficiency with bulk sugar is a stopgap. It is not a true solution.
I think we need to look squarely at the defining metric provided in the source material. The 50% reduction in outlier batches achieved through this 14-day kit. I want to build a structured argument around this specific figure, because in our field, this is not just a marginal improvement. In biomanufacturing, where failure rates directly translate into drug shortages for patients and massive financial losses for producers, cutting your outlier rate in half is a monumental achievement.
It is a significant improvement, I won't deny that.
The fact that this methodology can be deployed in just 14 days proves the strength and reliability of the framework. It means that the EM fingerprinting is fast, The PCA modeling is computationally efficient, and the SOP adjustment is immediately executable on the floor. You are looking at the 50% metric and seeing a half-empty glass. You're asking about hypothetical impacts on glycosylation, but I'm looking at a process that is fundamentally stabilized. When you combine the reduction in outliers with the explicit achievement of consistent peak titers regardless of agricultural origin, it demonstrates that the methodology is not just a temporary patch. It is a profound stabilization of the entire manufacturing lifecycle.
That's a compelling argument, but have you considered the ceiling of this methodology? If this 14-day kit with its EEM spectroscopy and PCA clustering is truly the definitive robust solution you claim it to be, why does it only capture a 50% reduction? The very term used in the source material, quick win, implies a surface-level optimization. In continuous improvement, a quick win is the low-hanging fruit. It is the easy fix you implement while you work on the actual deeply rooted problem.
Capturing the low-hanging fruit when it saves half your failing batches is just smart engineering.
But the fact that 50% of the outlier batches remain completely unaffected by this nutrient feed adjustment proves my earlier point. There is a vast amount of biological variability in corn steep liquor and peptones that simply cannot be captured by 3 mathematical buckets or fixed by bulk nutrient feeding. If we accept this 14-day kit as the ultimate solution, we are settling for a methodology that willfully ignores half of our failure rate. It is a highly valuable diagnostic step, certainly, but calling it a definitive fix is an overstatement of the data provided.
I'm not convinced by that line of reasoning, because it ignores the compounding difficulty of optimizing biological systems. Reducing unpredictability by half in any complex bioprocess is practically unheard of in such a short deployment window. Perfect cannot be the enemy of the good here. The methodology does not claim to rewrite the laws of biology or completely eliminate every single anomaly that could possibly arise from a plant or animal extract. What it does is systematically eliminate the most disruptive, high-impact variances that routinely derail production.
But it leaves the subtle, arguably more dangerous variances untouched.
By securing consistent peak titers across batches of completely different origins, the EM and PCA combination proves that it captures the most metabolically relevant data. And we have to consider that the remaining 50% of outliers may be due to completely unrelated operational issues. You could have sensor drift in the bioreactor, mechanical shear stress damaging the cells, or a microscopic equipment failure that has absolutely nothing to do with the raw material itself. We cannot demand that a raw material solution kit solve non-raw material problems. Within the scope of lot-to-lot variability, this framework is undeniably powerful.
But we must base our analysis entirely on the scope of the material presented, which frames that 50% reduction as a direct outcome of managing the lot-to-lot variability of the raw materials themselves. If we're categorizing raw materials into 3 broad clusters and still seeing half of the historical failure rate, it strongly suggests that the categories are simply too broad. The critical variability is slipping right through the cracks of the high, medium, and low definitions.
You think the clustering is hiding the real culprits?
Exactly. Perhaps a lot classified as medium contains a latent inhibitor. It does not affect the bulk EEM fluorescence significantly enough to shift the mathematical model into the low category, but it completely tanks the cell viability by day 10 of the culture. The quick win is real because it caught the most egregious, obvious deviations in the incoming materials. The subtle deviations, the ones that actually define the hardest challenges in biomanufacturing, require a much more granular approach than simply tweaking the macronutrient dial on the bioreactor.
I think that brings us to a very clear point of summary for our respective positions on this methodology. From my perspective, the integration of EEM fingerprinting, PCA clustering, and dynamic nutrient feed adjustments forms a precise, highly effective strategy. The material clearly demonstrates that this combination undeniably secures consistent peak titers and drastically cuts lot-to-lot failures by half in a remarkably short 14-day window. For me, it is a triumph of translating complex analytical data into actionable manufacturing protocols, proving that you can successfully engineer control over the inherent chaos of biological raw materials.
And my position remains that while we must acknowledge the immediate practical value of saving half of those lost batches, We should view this 14-day kit strictly as a valuable quick win rather than a comprehensive methodology. Reducing the immense biochemical complexity of peptones and corn seep liquor into 3 broad mathematical clusters and attempting to manage that complexity by merely tweaking sugar and protein ratios oversimplifies the true nature of living systems. It leaves a significant portion of process variability unaddressed and risks masking much deeper material inconsistencies.
Despite our different interpretations of the depth of this solution, it is clear that we share a significant point of convergence when it comes to the analytical technology itself. We both firmly agree that the implementation of fluorescence spectroscopy, specifically EEM fingerprinting, is a massive step forward for the field. Measuring and quantifying the optical signatures of incoming batches moves us away from blind reliance on vague vendor certificates, giving us direct, empirical insight into the raw materials before they ever touch a single cell in our bioreactors.
Absolutely. The application of EEM to capture the multivariate biochemical state of these complex inputs is a brilliant move. It is a level of analytical scrutiny that the industry desperately needs when dealing with agriculturally derived materials. Shining that light into the biological black box is vital. Our disagreement fundamentally lies in how we process and react to that magnificent data, not in the immense value of gathering it in the first place.
It forces us to reflect on the intricate balance we constantly have to strike in this field, the tension between engineering and biology. On one hand, we need actionable, rapid models that can be executed on a production floor today to save batches and stabilize commercial yields. On the other hand, we must maintain a deep respect for the profound complexity of the living systems we rely on, recognizing that a quick win may just be the opening chapter of a much longer story. The fact that a 50% outlier weight remains leaves immense room for deeper exploration and refinement of the methodologies presented in our source material.
Exactly. It raises the ultimate question of whether our brilliant new analytical tools will drive us to create more complex, highly dynamic control systems that truly respect the biology, or if we will continue to rely on the comfort of broad, simple categorizations. The data is finally there. How we choose to interpret and act on it will determine the next generation of biomanufacturing consistency.
A perfect place to leave it for today. We invite you, the listener, to weigh the evidence presented and consider where the balance truly lies between the undeniable practicality of actionable engineering models and the critical need to preserve biological complexity. Thank you for joining us for this intellectual exchange.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.